Hello, Disobey. My name is Ulf Frisk, and today I'm going to show you live memory attacks and forensics. I'm going to start with some live memory DMA, direct memory access attacks with PCILeech. We are going to pwn Linux and Windows with DMA code injection. We're going to mount their live file systems and spawn a system shell. I will show you live memory forensics with MemProcFS, and we'll have a look about what the MemProcFS is, and we'll go a little bit more in-depth look at its capabilities, its design, the API, and plugin functionality. Throughout the presentation, I will do demos, live demos, lots of live demos, so let's hope everything is working they usually do. My name is Ulf Frisk. I'm working as a pen tester by day, and since a couple of months ago, I started working for internal IT at Polisen in Stockholm, Sweden. And I try to do some security research by night as well. I'm the author of the PCILeech Direct Memory Access Attack Toolkit, which I presented at quite a few different cons before, including DEF CON, Blue Hat, and the CCC. Everything that I've been doing as 100% open source, and it really started back in 2016 when I found this really low-cost piece of hardware, the USB 3380. It had one side that was able to do PCI Express, and PCI Express is capable of direct memory access DMA, that is reading and writing the memory of a target, or if you want to call it a victim system. And it also had a side that was able to do USB 3 that allowed me to control this device from a controlling computer. And with this device, I was able to do around 150 megabytes per second DMA from the victim computer. Unfortunately, this device was only capable of addressing 32 bits, and this meant that it was only able to read memory below 4 gigs. That was kind of boring. But at that point in time, back in 2016, that didn't really matter because it was sufficient to pwn most of major operating systems anyway. But things change, and computers, they usually do have more than 4 gigs of memory. So that's why I introduced a little bit over 2 years ago public FPGA-based DMA attacking at the CCC. And now we're able to attack the whole memory space and read all memory of the computer pretty much. So this is how my two tools that I will be talking here today about will relate to each other. We have the PCILeech, which is really focused on attacks and red teaming more. And we have the MemProcFS, which is high-speed memory analysis and forensics. They both use the same backend library, which allows me to capture physical memory from various kinds of memory sources. The hardware sources, I can also use WinP memdriver or dump it to capture live memory from a running system, or use read various dump file formats, memory dumps. So let's do our first demo for today before we start getting into the specifics. Let's have a look at Linux. I'm going to use a hardware, the Screamer M2 board, which is really a really small FPGA board. It's in the M2 key M form factor. And it has one side that is PCI Express and one side that is USB 3. So it allows me to do DMA. And in Linux, let's implant a kernel module into the running kernel with the help of DMA. And let's mount the file system, and via the mounted file system, we are going to try to unlock the computer. If we switch to the computer, there it is. And this computer, it's like a Kali Linux. It's fairly recent. It's not the most recent. It's the 2019 4 version, so we still have the root and Kali. It was a root and Tor. So, but we pretend we don't know that the password is Tor, so we try to single A here. Press that button. And as you can see, we cannot log on to this computer. This is very boring. If we don't know the password, it might be a better password than Tor. So that's why we are inserting our FPGA device, the one I showed you. I'm going to use Express card here today for convenience. I'm inserting it in this target system. And if we switch to my presenting computer, also, I'm going to load a kernel module into running Linux system if everything is working. We seem to have being able to read some memory at least. Code execution, successfully inserted kernel module at this address. And now I inserted a piece of code into this running Linux system while the computer is locked. And this is pretty much the default configuration for Kali, by the way, that this is possible if you do have PCI Express access. So let's use this kernel module in order to mount a live file system. I'm going to specify in the mount command the address of this physical address of this kernel module that is loaded. It says that it's mounted as drive K. So let's click into and do some point-and-click attacking. And here in the root, I do have the live RAM here mounted as files. And if you do, you can just copy the files in Windows Explorer, and you have a complete memory dump of this Kali Linux computer. And in the files folder, we see the root folder of the Linux system mounted. And since it's the root folder, I mean, everything in Linux is pretty much a file. So you can actually copy the disk drive if you do a copy in Windows Explorer of DevSDB, for example. But let's not do that here today. Let's go into, no, not in the dev folder. The etc folder has some really interesting files. For example, if we want to change the password, we have the shadow file. That's a really special file in Linux. And since we are running as kernel, we do have like the highest privileges. We have more privileges than root even here. So we can read pretty much any file. So let's open it in Notepad. And here you see the root password for the root user, or the root hash to be correct. And you can take this hash and try to crack it in a hashcat, for example. And if you do have a really good password, I mean, you won't be able to crack it probably. But it's much easier to just replace the password hash of the password of single A. So let's do that. It's a really long password hash. But let's hit save here, and let's close this notepad. And actually, I'm going to close this one as well. And if we switch back to the Linux computer, yeah, we have it on screen. It's the screensaver that's running here. And we see if we have the password hash of single A here, if it's working, the password of single A. So we are logged on. If you switch back to the presenting computer, awesome. Linux security, it can be really good, or it can be really bad. It's like totally dependent on which distro you're running. And in most cases, like more privacy-focused distros like Cubes, they're going to be by default totally secured against this. Other vanilla Linux distros might not always be. If you're like concerned, I would still recommend like using hardware without any DMA ports, like the easily accessible. And it's always good to set the BIOS password. You lock down your DMA ports in BIOS or UEFI if you're not using them. And also having a decrypt passphrase is always nice to have for security. But really, the long-term solution is to actually use some hardware that is already existing within your computer. That's like the IOMMU and the VTD, which is virtualization-based security that the operating system will start to use this, and Cubes do, for example. What makes this possible is PCI Express Direct Memory Access DMA. And traditionally, PCI Express devices have been able to access the physical memory straight out without any restrictions. That's since a really long time ago. And that's really unlike code that you're executing on your CPU, which usually execute in virtual address space. And in the border between virtual address space and physical address space, you have a memory management unit that is doing the translation from virtual addresses into physical addresses. And this is pretty much what upholds the security on all modern-day computing systems, is this memory management unit. You wouldn't be able to do like process isolation or hypervisors and things without this one. But since around 10 years ago, there exists a memory management unit for devices as well in the hardware on most new CPUs. But the operating systems and the firmware haven't really been using this IOMMU to its full extent in order to protect them against DMA attacks. So if it's not used, we can still do the attacks. PCI Express comes in quite a few different form factors. You have the standard PCI Express one to the lower left. You have the mini PCI Express Express card, for example, that is starting to get a little bit old nowadays. Thunderbolt is pretty much external PCI Express, and you do have the M2 key form factors, which is more common nowadays. You have the M2 key M form factor, for example, which my attacking device has that form factor, but also NVMe drives, so it's really common. So this is how it works. On my analysis computer, I do in software create a PCI Express transaction layer packet. PCI Express is packet-based. So I create a memory read packet in this example. I wrap it in some extra metadata fluff, which allows me to transmit it over USB 3 towards the FPGA board. Once the PCI Express TLP reaches the FPGA board, it sees that here comes the TLP. Let's put it on the PCI Express of the target system, Express card in this example. And once the TLP packet reaches the PCI Express root complex of the target victim system, it's going to see that we want to do a memory read here. So it will read the main memory and respond with the memory read in a completion packet containing the data, which is transmitted back to the FPGA and back to the analysis computer. So let's have a look at Windows as well. Let's execute some code and hopefully mount the target file system. And let's, if everything goes well, spawn a system shell as well. So I'm going to, yes, switch to the attacker computer, awesome. And here I have a Windows running. It shouldn't be. And we type the single password of A here again, as you can see. And we cannot log on this user account on this Windows computer. And this is the most recent Windows 10 1909 on like a pretty old laptop, but I haven't been configuring anything special. So it's like a pretty much default install. I added BitLocker to it, so it's like, but that's about it. Let's change that. So let's insert our FPGA device once again and switch back to representing computer and see if we can load a kernel module into running Windows system. Oh, that was fast. And the computer actually seems to be working still, so that's kind of nice. So let's mount the file system of the Windows system. And as we are using the kernel module, we are running as kernel here, so we should be able to see quite a lot in this Windows file system. If you have a look at the root folder, we see the memory as files as well. If we here again, if we want to copy it, but we can also click into the files folder, and in the files folder, we are able to click around here with the privileges, file system privileges of kernel. So we have a really high privilege, so we can click into the user's folder, for example, and we can spy on his files, and with some interesting files here on the desktop or something like that. And since I can also save to files, obviously I can gain code execution by editing some files or do other evil things here. But it's more fun to spawn a system shell. So let's do that instead. Closing this down, and let's spawn a system shell instead. So let's check who we are, and we are system here. Over PCI Express. And this is a little bit unstable, but let's try again. Net user A is going to change the password net user, and then I'm specifying the user account and then new password. So I'm copying that and starting the shell here. It doesn't like me here today. Come on. And switch to the Windows computer now. And I'm trying to log on here. So let's see a password of single A. Enter. And switch back to the presenting computer. Windows security in Windows 10 is really dependent on your settings and your hardware and the configurations between that, and I'm not going to go into detail here, but Windows can be made quite secure as well. Microsoft is investing a lot in virtualization-based security, and that includes the IOMMU and the VTD we talked about earlier on. They also do things like on some PCI Express buses, they disable new DMA devices when the computer is locked. And they also have things like hypervisor-assisted code integrity that in some cases it will only allow me to read executable pages within the kernel, but not write to them, which makes it a lot harder. They also have like initiatives like Secure Core PC. They just released some months ago, I think. I haven't been able to take a look at them yet, though. But still, if you're running Windows, I would recommend you that you do use a BitLocker pin and just not only relying on the TPM in an auto-booting configuration. Having a pin there really makes a huge difference for an attacker. Let's talk about memory forensics as well. Let's talk about MemProcFS, which is the memory process file system, which is really memory forensics done in a completely new, different way. It's Windows, heavily focused on Windows. It allows you to visualize in-memory Windows objects as files and folders in a virtual file system. It's multi-threaded. It comes with a C core, and it has some really intelligent parsing in there, which makes it super fast. You can use both hardware-based memory acquisition, I just showed you, but you can also analyze memory dump files, for example, or acquire live memory using drivers. So why do you want to do memory forensics? I mean, this is my take on it in a really few sentences here. You might want to capture the running state of a system that includes like running processes, open network connections to like CNC servers and things like that, because not everything resides on disk. Example of things like that might be like in-memory malware, in-memory only malware that might not reside on disk, and you also have like crypto keys, for example, BitLocker AES keys, and things like that are floating around in main memory. So let's do a demo on the memory process file system, MemProcFS. We're going to mount 128 gigabytes in just a second, or a few seconds. So I have a folder with dump files. I have an Umbrella Corporation computer here that's like 128 gigabytes big here. It's a quite big memory file. If you've done memory forensics before, you know that this might be a challenge to analyze. So let's open it by double-clicking on it. And it says it's initialized. And now I mounted the memory dump as files and folders in a virtual file system. In the root folder, you do see the physical memory. It's really uninteresting in this case, since we mounted the physical memory or a memory dump file, so this file is going to be totally equal. But if you're acquiring live memory from FPGA devices, this might be super interesting. Also do automatically create WinDebug-compatible memory dump files, so you can actually do WinDebugging on raw memory dump files or live memory as well. If you do like that, so let's try to run a command to see if it's working. Yeah, so it's like looking through a lot of things here. We have a folder which is called sysinfo, which contains various kinds of information about the system, for example, the version information of the running Windows system. We have a proc folder, which contains like a process tree information of the process, the PID and the parent PID, and also which user is running this process. And you see if it's running like a local service system, or the user seems to be like a John Smith user on this system. We also have a verbose view that contains a little bit more information. We have like the path to the executable that the kernel sees, and this is really interesting if you're doing like malware analysis, because user mode malware cannot modify this because it's in the kernel. These two values below, which might in some instances contain the command line arguments, they are in user mode, so they might be a little bit more untrustworthy. You have the network connections, like a netstat view of things, and you also see the process, which is like having this network connection. Registry is a huge part of Windows system. All applications store their configurations in there. I do reconstruct the Hive files. It's like not going to be like a complete Hive, because not everything is actually residing in memory. Some things might reside on disk, but it's like I'm doing a best effort reconstruction. So it's pretty good, actually. You can go into each Hive. You can click into and have a look at it in a file system. But let's go into the machine Hive and software. And I think we have like Microsoft, Windows, current version, run. There's usually some interesting stuff in there. and have the some value here that's called the security health that's going to be running when the computer is starting is normal. I have the raw view that is in the registry, but I also have like a text view for the user to view in an easy way. So it's like point-and-click memory forensics. We can also go into like the users, and we have the John Smith user here, and not. We have we can click around in the users. We have the volatile environment, for example, which is going to be registered keys that only exist in memory, things that you will never find on disk, things that are like virtual keys in memory only. So you can analyze those ones as well. You can see like things like username and logon server and things like this in this case. If you're more on the offensive side and want to do evil things, there's some good news. I got some awesome contributions from a guy called Skelsec, which is making an open source version of Mimikatz in Python as a library. And so you can actually use this Pipikatz to, and it's included as modules within this MemProcFS file system, as you need to download them separately. But you can, now this is a standalone computer, so it won't have like the ticket granting tickets here, but they will show up as files to just copy. And we can go in and have a look at the other accounts and password hashes in some instances. We can go into the reg secrets folder, which contains more like the password hashes of the user stored in like the, is in the standard format if you want to crack Windows password hashes from the SAM, for example. But most interestingly, we do have a folder for each process as well. It's either sorted by PID or sorted by name. So let's click into the 7-zip process, for example, and do some analyzing of this one. We have the total virtual memory as a file. It's going to be zero-padded if there is no virtual memory in that place, but you can actually edit the virtual memory in your favorite text editor. If you change stuff, it's not going to work if you run against like a memory dump file, which is going to be read-only, but if you're running against like live memory with the PCILeech, for example, you can write to it as well. And for each memory segment, I show you it as a separate file as well, if you prefer that view. And user information, we have this, seems to be John Smith is running the 7-zip. We have the SID and a few other information about this one as well. Information about the threads, and we have the stacks as files, both the kernel view of the stack and user mode view of the stack, and you can edit these ones in your favorite tools as well. Python plugins as well, and modules, like every loaded DLL you have in each process here. You can click into it in the file system. For example, you can click into the executable, the exe, and we are going to see exported functions, imported functions. We can actually have a look at the imported functions. You see which function addresses from which DLL they are imported from, and so on. And we also can edit different sections in the loaded DLLs and the exes, and this is writable as well. Memory maps can be reconstructed by either, something called virtual address descriptors, VADs, and contains a lot of information. It's like how Windows keeps track of it, or we can walk the actual page tables that the CPU uses when it's executing code or reading memory. And this is interesting because malware has a really hard time of spoofing this. So if malware wants to execute on the CPU, it really needs to have an executable page within memory. So there's really no way of hiding from this, because then the CPU wouldn't execute that piece of code. Handles is like whenever you open a thread, process, whatever registered key file, Windows is going to open a handle. You usually use like close handle API call to close the handles. Information about those ones, and various files constructed either from the handles or modules or VADs and whatever. And this 7-zip is not really interesting, but let's have a look at some other process. We know that, for example, some of the SVC hosts are going to have, let's see here, yeah. We are going to mount the drive in Ubuntu. And Windows Linux is really nice, by the way, if you're going to do some stuff here. We know that the SVC hosts, one of the SVC hosts is going to contain the event log files. So let's do like ls in Linux command prompt for this ones. It seems to have some event files in process 1696. So let's see if we go into names folder, SVC host, 1696 it was, files, handles, and here we see lots of event log files. Now I can't open this in event log viewer straight away since it wants to create a temp file, but we can copy the file. And now we can try to open it. Might take a short while. We see that there seems to be some number of events in here, for example, and this is really interesting if doing memory forensics, and it's usually not the whole event log file since it's only going to be partially in memory, but the positive news is that the most recent data is actually going to be in memory. So you can click around and have a look at events here, and this is acquired from the RAM of the target computer. So how is it done? First, I want to say my overall design goals. When I created this, I wanted to have something that was super easy for everyone to use, that I could use myself, but I wanted it to be powerful still. I wanted to have the design modular and have plugin functionality to allow others to contribute plugins and other awesome functionality to this project. And I wanted to have APIs. And since it's coded in C, it's going to be a C API, and that's quite portable. But also Python is really popular within the security community, but also the memory forensics community, so add a Python API as well. And performance is super important, and because when you're clicking around in a file system like this, you really want to at least have it to feel like really quick and nice like that, so you don't have to wait for a couple of minutes for things to happen. So how is it done? For the file system part, I use a third-party library, which is called Doken. It's like a super awesome user mode file system component for Windows that's available as open source on GitHub. It takes care of the hard part, such as having like a file system driver in the kernel. And all I need to do is to implement some really simple user mode callbacks in my memory process file system executable, which is just a very thin wrapper around the main analysis library, which is where all the memory analysis is taking place. I do have plugins in both C and Python connected to this, and also a Python API. And in the backend side, I use the Leech core library in order to do physical memory acquisition from a various range of devices. So this is how the analysis library is built. On the very top, I do have the API that all applications that want to use this is calling into, and that's including my memory process file system executable. On the very bottom, I do have a very simple layer of an object manager, which allows me to keep track of things like object reference counting, and this will allow me to do more easily be doing like multi-threading. On top of that, I have a layer of caches. I have a separate cache for physical memory and a separate cache for page tables. And caching, even though memory accesses might be really quick, like below 1 millisecond for each access, if I'm using the FPGA, for example, if I'm doing thousands upon thousands requests, it's going to be really slow without an in-memory cache anyway. On top of that, I have a virtual memory to physical memory translation layer, which is going to be able to translate the different memory models that Windows do support, the 32-bit ones and the 64-bit one. Also, I do include like support for Windows 10 compressed memory in here, which is a nice thing to have. And then I have the main analysis part. I do various kinds of analysis in here. I do have the notion of each process is going to be an object, and each process is going to contain like what I call the maps is really collections of other objects, for example, memory segments, these VADs, DLLs like loaded modules. Also have the plugin manager, external plugins, we already talked a little bit about them. And also I do have like internal built-in plugins, which allows me to abstract some things in a nice way. And also have some background threads in here that's doing like housekeeping tasks, like refreshing the cache and things like that. The Leech core library, it's used by both PCILeech and MemProcFS, and its focus is physical memory reads and writes, and it allows me to separate memory acquisition from analysis in a really nice way. It does support the original USB 3380 device that I used, the FPGA devices. You can acquire live memory using drivers from a running system. I do support WinPMem and dump it at the moment. I do support acquiring memory or like reading memory from various dump files. For example, full crash dump files, which is created by dumpit, for example, but also raw memory dump files and Hyper-V save files. About a year ago, also got a really awesome contribution from Synactive. It turns out if you have a really old HPILO, you might be vulnerable for some remote exploits against this HPILO. And if you run some old exploits against this, you can implement or add like Synactive's DMA backdoor into this HPILO, and then you can use the Leech core library in order to read and write memory of the target operating systems in there. Also, I do support connecting to a remote Leech core instance running as a service on a remote computer. And if I'm doing that connections, it by default is going to be secured by Active Directory, by Kerberos. It's going to be mutually authenticated connection, which is encrypted and also compressed. And once connected to this remote Leech core instance, I'm going to be able to use all the above memory acquisition methods, but on a remote computer. In most practices, like I think the dumpit and WinPMem approach is most interesting in there. So let's do another demo. Let's do some live memory analysis and also alter the memory of a running system. Let's hunt for some data in the process heap, and let's overwrite that data in the memory. So yes. If we switch back to the other computer here, awesome. And here I have this computer. I don't have the notepad started here or anything. Let's insert our FPGA board into this one and switch back to representing computer. Let's mount the file system again. So it's mounted. Switch, awesome. Here we have it in the names folder. Let's see if we have the notepad started. We don't have a notepad here because we never started it. So if we switch back to the Windows, the other computer, awesome. And we're going to start a file here. So hello, Disobey. Switch back to the presenting computer. And I'm going to do a refresh here and see if in notepad it appears here. And we think that the data, hello, Disobey is going to be in the heap somewhere. We have like stacks and heaps in this vmemd subdirectory. And so let's have a look at this. So let's mount that in the Windows Linux and go into the vmemd folder of the notepad. And have a look if we can find some heaps in there. We find a couple of heaps in there. And we suspect the text is going to be on one of them. So let's do strings on the heaps. And we have one candidate. So let's open that heap file in our hex editor. And let's see if we can find that data. And I'm going to search for the text in hex ASCII, and it's going to be 0 padded every second byte because of UTF-16 Lithuanian, but we seem to have some text here, hello, Disobey. So let's try to change that text. To Helsinki. And we're going to hit save. Want to save changes? Yes. Switch back to the other computer. And it didn't change the text here. That's a little bit boring. But it's just because we need to click somewhere to update the frame buffer. So and you can, of course, do this on like executable code as well and change it on the fly and do interesting things like that. So you can also use this for basic incident response with this remote agent I was talking about. Imagine if you do have a suspicious process on some computer, and you might have quarantined this computer to a quarantine VLAN. But you might have really limited bandwidth and high latency to that remote network, and a full memory dump might just take for ages. The solution might be to retrieve only the memory you actually need and analyze it with MemProcFS. Or even better, you can actually run the analysis on the remote computer by submitting a tiny Python script. We have the Python API functionality. You can do pretty much everything in this. You can read and write memory, both virtual memory and physical memory, various process and modules information, information about the registry, and if you want to use like PDB files from Microsoft Symbol servers, you can do that as well. And also, you can read and write and list files in this virtual file system. Even the virtual file system is not mounted, it will still reside within this analysis library, and you can use the API to list files in these virtual directories, read the files, and write to the files. So let's do some remote malware analysis and analyze the live memory from a remotely infected system by clicking on Files and using the Python API. So here I have a remote system. It's like in the Evil Corp. It's in Active Directory domain here. It's running on my computer. I have a domain controller here. But this infected computer is really sad. We suspect there's something wrong with this, and it's not going to be all the toolbars the user installed here. But we don't know. We have a blue team computer as well. The blue team user that is logged on is actually an admin on this remote system. So let's try to install this remote agent to this remote system. So I'm going to do a remote install, and it's going to connect to the service manager. And since I'm admin on that computer, it will allow me to install a service on this computer. And it's going to start like a listening on incoming TCP connections. And this connection is going to be secured by Active Directory Kerberos, and only administrators are allowed by default to connect to it. Now we can start the memory process file system against this remote computer, and we're going to use the pmem driver, WinPmem driver, to do that. So now we can click in there, do memory analysis on the fly. It's only going to acquire small amounts of memory from this remote computer as we go. And we have an evil process here. I know it since before. This is not a friendly process. It's some malware that I happen to infect this computer with on purpose. And and we can do things like running pipicats against this remote computer as well, of course. But let's have a look at the Python API instead. So let's open Python. Helps if I'm spelling correctly. So we are going to import the library. And let's have a look at the files, the API calls. We have quite a few of them here, but we need first to initialize. And now we are connected to this remote agent, and this remote agent is going to take like simultaneous connections, so that's not really a problem. It's just that we initialize the Windows system here. So let's retrieve, for example, the PID of the explorer.exe and print it on the screen. It seems to be this PID. We can retrieve process information as well, and for all processes. And let's have a look at it for the Explorer PID. We have some useful information here from this live memory that we are analyzing, and you can analyze memory dumps as well, of course. And if you want to have it look at all process information, that's going to be a lot of information, of course. But now we can do, with this information, we can do a process listing of the processes in the active system. Quite easily by coding a small Python line. We can have a look at the memory maps. We are going to have a look at the Explorer memory map, and we're going to have a look at entry number 300, since there's quite a few entries in this memory map. So this seems to be like some entry. It doesn't have like a special module assigned to it. It seems to be a read-only memory. And we have the virtual address and some things like that. But now we can write our small Python program. So for each process, we're going to iterate over the PID and the process information. And for each process, we are going to retrieve the memory map. And for each entry in the memory map, we're going to check if it's read, write, execute memory. And we're going to print it on the screen together with the PID. And we are going to only be printing 2 entries per process maximum, since it would clog the screen otherwise. So now we are retrieving memory on the fly from the remote computer as we go, and we are walking through all the page tables of all the processes in that target system and we're already completed. And we see so we have some read, write, execute memory in our evil process here that we know, for example. And we can do things like retrieve physical memory here as well, virtual memory, read memory, if we want to do that. So, but imagine if this connection it might be really slow, and reading from this remote system, latency issues might be problematic still, even if we retrieve like tiny amount of data. We might want to submit this analysis script to the remote computer instead. So here how it looks like. And we can use the PCILeech agent exec Python command in order to submit this to this remote instance. So now we send the script to remote host, and we are analyzing on the remote host. It's going to spawn a child process, do the memory analysis in there, and since we have a local connection on that remote computer, the infected computer is going to be super fast. And we already see the result here. So another use case for my tools is something that I never anticipated myself. I think it's a little bit funny, but it's hardware cheating in games. It turns out that anti-cheats, they're really powerful pieces of software that detect most, if not all, software-based cheats. And a hardware cheat might only be seen as a PCI Express device in the target system. And you kind of need to have PCI Express devices in order to do serious gaming. You need to have graphics cards and things like that. You can do things like read-only hacks, like wall hacks, radar map decloak hacks, or if you're doing writing, it might be a little bit more easily detectable. And this is how it looked like back in 2018 when it was really popular. It was like touted as undetectable cheating within the gaming community for a short while at least. And this is the PCI Express streamer device inserted in a gaming PC. But it's not really undetectable. It was initially really easy to detect, actually. It took a while for the anti-cheats to catch up, but ISEA, which has a really good anti-cheat, they catch up kind of quickly, and when they did, they started banning players, of course. They claimed that the prices for these cheats had been selling in around $1,500 to $5,000. My stuff is open source, and I never saw a cent of those money, but anyway. And of course, it resulted in a ban by both cheat customers and developers. And initially, it was really easy to detect because most of the cheaters were using my standard FPGA bit streams, which has some like hard-coded device IDs in there, which is really unique. And if you have this device when you're playing CSGO, for example, I mean, you're 100% cheater pretty much. So it's like, of course, they got banned. But they also claim that they're able to detect hardware-based cheats, even when disguising the hardware cheat as a legitimate device. I don't know if that's true in all cases, but it certainly makes things a lot harder. When I'm looking forward, I want to add more functionality for the MemProcFS. I want to add more plugins, and there's like a plugin API there, so if someone wants to help, have an awesome idea for a plugin, it's like I would really like really welcome plugins. But my priorities, I want to add like process mini-dump files kind of soon. I already had a full kernel crash dump file, but I want to add like mini-dump file for each process as well, and I want them to be analyzable in like WinDebug. Also add some better networking support, like UDP connections. I don't see them at the moment. It's only TCP. Also, I think I need to add like background scanning of memory dump files, because now I read memory as I go only, because that makes it really quick, but I will miss some things. And if I'm doing like background scanning, it shouldn't be affecting the user too much. And if you're doing one pass, and it could run in the background, and yeah. And I want to do things like page hashing, which would allow me to look up things against an online database and also recover of some artifacts that are missing. I want to add timelining and also try to recover files from the master file table. I also add APIs for PowerShell and C#. So when I'm looking, people have been asking me about this one. I don't really like comparing my tools to other tools, and I think, but people have been asking so much about it. So I think volatility is really also memory forensics is the industry standard for it, and I think my tools at the moment, it might be a complement if you want to take a quick look at things, since it's quite fast. Obviously, if you're doing memory forensics on other operating systems than Windows, my stuff is not an alternative. So, and I try to focus on an easy-to-use file system that allows pretty much everyone to click around in it, and you shouldn't have to know a lot about memory forensics in order to do memory forensics. But I also have a C API and a Python API. Volatility is more like command line approach. And, but it's coded in Python, so you can do a lot of stuff in Python as well. I do rely on fast, efficient in-memory objects and parsing a lot. Volatility, it's a little bit slower, but it's also more comprehensive in some ways, memory scanning approaches. But it's like they catch a lot of things that I miss, and I actually catch some things that they miss, so maybe use both tools. And really what makes MemProcFS shine, I think, is the integration with the PCILeech live memory capture with the FPGA devices, and also that it has like really transparent Windows 10 memory compression support. Volatility, I mean, they have a huge support for a lot of plugins and functionality that I will never. So like it's really awesome to continue using that as well. But in order to sum everything up, MemProcFS is fast. It's super fast. It's easy to use. It's really point-and-click memory forensics. And acquisition, you can capture memory using the memory dump files. You can actually analyze memory dump files. You can use the driver approach with WMP memory and dump it, the FPGAs that I showed here today, or the remote agent. Plugins and API, roll your own plugins in C, C++, or Python at the moment, and everything is 100% open source. And thank you.